So today I'll be telling you all about some of the work I've been doing with Ravenel-Wilson Hopf-ring methods in C2 equivariant homotopy theory and computing some of the HF2 homology of C2 equivariant Eilenberg-MacLane spaces. So this is an equivariant homotopy talk. So what are we studying? We're studying spaces with a G action. So some examples would be spheres with different types of actions. We could consider S1 with the antipodal action or S1 with the conjugate action, thinking of S1 as living in the complex plane. And these would be some examples of the sorts of spaces we're interested in. If our spaces have a G action, our maps should then be G equivariant. So if you maybe haven't thought about equivariant things in a little while, if we have some group G, maybe G is an element in G, and we have some map going from X to Y, this is going to be equivariant if f of G acting on X equals G acting on f of X. And well, this is a topology seminar, so we're probably all familiar with the notion of homotopy as a continuous deformation and what that is. Here, our homotopies will also have a G action where the action on the interval is trivial, but otherwise they're equivariant. So within this setting, one of the invariants of interest to study is ROG-graded homology. And throughout this talk, our group G is going to be a finite group, but we can also do computations in the setting where G is compactly. There are just a few things that are a little bit more complicated in that setting, so I'll be sticking to finite here. And in this finite group setting, we're going to have consider spheres that have reflection and rotation actions. So to get these spheres, we consider the real representations of our group G and form the one-point compactification of that space, giving the point at infinity the trivial action to get a representation sphere. And then we grade our homology or cohomology on the real representation ring, and this is called RO of G. Really, we're grading it on the underlying additive set, as opposed to using the multiplicative structure since it's a grading. But what does this mean in a specific example? Well, let's consider the group G equals C2. Throughout my talk, all of my computations are going to be C2 computations, so this is also the most relevant example for this particular talk. We'll be seeing some more examples later on this week. So C2 has two irreducible representations, the one-dimensional trivial representation and also the sign representation. So we can think of the one-dimensional trivial representation as having no action on the real line, and the sign representation as something that interchanges the signs. So then taking the one-point compactification of these two representations, we end up with two spheres, S1 and S sigma, which has the conjugate C2 action. And then we're going to grade our homology on these two types of spheres. And we'll denote that with a 5-point star as opposed to the more typical asterisk sort of star in the non-equivariant setting. And if you don't think about equivariant homology a lot, one question you might have is why consider ROG-graded homology? And one answer to that is, well, the geometric motivation for homology originally in the non-equivariant setting is to look for different types of holes or spheres inside your space. And here we're really doing the same thing. We just want to keep track of more information. We want to keep track of holes that have some sort of rotation or reflection information as well. So when doing ROG graded computations, one of the first things you run into is that the homology of a point is much more complicated than in the non-equivariant case. So if we're considering the group C2, we have our two irreducible representations that we're grading on. So in these axes, in these pictures, the vertical axis is the number of sign representations, and then the horizontal axis is going to be the topological degree, so the total number of representations. And the homology of a point works out to be an infinite dimensional non-Noetherian ring. So in this picture on the left-hand side, we have a picture of the homology of a point where each of these dots represents a copy of F2. And this has some distinguished generators, A living in degree minus sigma, U living in degree 1 minus sigma, and theta living in 2 sigma minus 2. And the picture on the right-hand side is also another representation of the homology of a point. We're simply not drawing all of these lattice points. So in this more complicated setting, what is some of the motivation for doing additional computations here? Well, invariance in equivariant homotopy theory can have powerful applications. Some of them include applications that Hill, Hopkins, and Rapinelli used to solve the covariant invariant 1 problem, and then equivariant and motivic applications that Dan Isaacson and co-authors have been using to compute differentials in the atom spectral sequence. But despite these powerful applications, many computations remain difficult to do because of all this rich structure that we're trying to keep track of with the G actions. So what we'll be talking about today is an extension of Ravenel-Wilson-Hofring techniques to C2 equivariant homotopy theory. And our main motivation and application of this will be computing some of the ROC2 graded homology of C2 equivariant Eilenberg-MacLane spaces. Along the way, we'll also study some ROC2 graded bar and twisted bar spectral sequences. So some background on this problem. Non-equivariantly, Sarah applied the Borel theorem to the past space vibration to compute the cohomology of the nth plus first Eilenberg-MacLane space given the cohomology of the nth Eilenberg-MacLane space. So this was an inductive sort of calculation. And equivariantly, this works to study trivial representation d-loopings. So spaces kV plus 1, where here V is some C2 representation, and we're adding a trivial representation to this. So specifically, loops on kV plus 1 is going to be kV. However, C2 equivariantly, we also have the sign representation. And so if we're going to consider an inductive sort of computation or argument, we really should also be calculating computations for spaces kV plus sigma as well. So we introduced these Ravenel-Wilson-Hofring methods in order to study these sign d-loopings because it has been hard to get a handle on them using other methods so far. So that's a bit of the background on this problem. At this point, are there any questions? Okay, great. So I'll now get into some of the classical Ravenel-Wilson-Hofring techniques that we're going to be extending to C2 equivariant homotopy theory. So first, let's recall what a Hofring is. A Hofring is an object in the category of graded co-unital, co-associative, co-commutative co-algebras, or at least for me, it will be graded. It doesn't have to be graded. But as such, one consists of a sequence of abelian groups, which we could call M sub I. And each of these are going to have a coproduct And we'll also have a graded multiplication, here denoted with the circle product. And one place hot springs arise in homotopy theory is in the study of omega spectra. So we could consider an omega spectrum G. This consists of a sequence of spaces together with some structure maps between them. And this represents a generalized cohomology theory, with the cohomology of a space X being equivalent to the homotopy classes of maps from X into G. And since the kth cohomology of X is an abelian group, this is going to mean that the space GK is abelian in the homotopy category and moreover is an H space. Really, it's also an infinite loop space since we started with an omega spectrum. But at any rate, this H space structure, here denoted with a star sort of asterisk, this gives rise to a product in homology. And if we require that the homology theory E that we're considering has a Kunis isomorphism for the spaces GK, making the E homology of GK into a coalgebra, this gives the E homology of G all of the structure of a Hopf algebra. So that's great, but we can have and ask for even more structure. We can consider spectra G that are a ring spectrum. Then the cohomology is also going to have the structure of a graded ring, and the multiplication given by the cup product is going to have a corresponding multiplication, here denoted by the circle product in the spaces GK of the spectrum. And then once again, we can apply our homology theory E and get a circle product in homology. And this makes the E homology of G a Hopf ring. So the example where, Ravenel and Wilson used these two products, the star and circle product, to construct many elements from just a few. And this was an idea they pursued in a number of applications. They used it to successfully compute the mod P homology of classical Eilenberg-MacLane spaces, the Hopf ring for complex cobordism, and the Morava K theory of Eilenberg-MacLane spaces. So the example we'll be focusing on today will be this first one, the mod P computation. And to set that up, we'll want to consider the Eilenberg-MacLane spectrum for FP. So we have this Eilenberg-MacLane spectrum denoted HFP, and the spaces of the spectrum, which are Eilenberg-MacLane spaces, and I'll simply call them Kn. And up to homotopy, HFP is characterized by the cohomology of a space X being equivalent to the homotopy classes of maps from X into Kn, and this gives rise to a star product. Also, HFP is a ring spectrum, so we also have a circle product. And mod P homology has a Kunis isomorphism. So we have all the things we need in order to know that the homology of the Eilenberg-MacLane spaces is a Hopf ring. So that's great. We know it's a Hopf ring, but which Hopf ring is it? And Ravenel and Wilson used a number of computational tools in order to track down exactly which ring this is. And one of them that's of primary importance is the bar construction. And they used the bar construction because it is a trivial representation de-looping functor, meaning that if we apply the bar construction to the nth Eilenberg-MacLane space, we'll get the nth plus first Eilenberg-MacLane space. So I have the precise definition of what this bar construction is written down, but how I would like us to think about it is with the following model. So we're going to have some topological monoid A, and our bar construction is points in an n simplex with we can think of it as labels in a mod some equivalence relation. And so one way to model this is to think of the points in your simplex as giving coordinates on the interval. And I'm going to consider the slightly non-standard interval -1 to +1. The interval 0 to 1 is a little bit more common, but this one will be nicer for our modeling purposes because then when we introduce a C2 action later on, things will nicely rotate around the origin. So we're thinking of this as having labels in our monoid A. And this space is then topologized. So this is like what a point looks like in this. And this is topologized so that as points in the inside of this interval come together, if they come together and collide, you simply multiply the labels. And if it falls off to the boundary, the label gets identified with the identity in your monoid. And one of the nice things about thinking about the bar construction this way is it allows us to give a very explicit description of a star product. So suppose we have some other point. Maybe we just have one point in our simplex and one label. Then the star product on this is going to be given by simply overlaying the two intervals. So we have T1, T3, T2, A1, A3, A2. And here it's important that for this particular model of the star product, it's important that your monoid is actually commutative. In the cases we'll be considering it is, because that way, in case the labels overlap, you know which order to multiply them in. Okay, so we have the bar construction, which gives us a way to construct the nth plus first space from the nth space, but what we're really interested in is in computing homology. And something that's useful for computing homology is spectral sequence. So this leads us to the bar spectral sequence. So something we can do is we can filter the bar construction so that we only take pieces that have something in simplex topological degree T or lower, and take the associated graded pieces of that, which are T spheres smashed with T copies of our monoid A. And then we can apply homology to these filtered spaces to get the bar spectral sequence with E1 page given here. And this bar spectral sequence will compute the homology of BA. So some useful things to know about this bar spectral sequence is that it has a very nice E2 page. In particular, E2 is given in terms of a Tor functor. So it's something we hopefully know and are a little bit familiar with from homological algebra. So to get this computation running, it's helpful to know the homology of K1. So in the case that the prime we're at is 2, K1 is just RP infinity. And at odd primes, it's going to be a lens space. So I believe the homology computation is in Hatcher, among other places. And this turns out to be exterior on some generator in degree 1, tensored with something that's a divided power algebra on something in degree 2. And then since we're working with FP coefficients, this is going to be equivalent to, well, we keep the exterior portion written the same, but we can write the divided power algebra as a truncated polynomial algebra on some generators gamma p to the I of alpha 0. So here we're taking the tensor product over all I. And because this is a little bit unwieldy of a name, I'll give these the names alpha parentheses 0. So our homology of K1 is exterior and truncated polynomial, where truncated polynomial means T adjoin X is defined to be Fp adjoin X mod X to the P. So in the case that our prime is 2, this is simply an exterior algebra. Okay. So what's useful about having the E2 page being a Tor term is, well, we know how to take Tor over an exterior algebra. That's a classical homological algebra computation, that Tor over an exterior algebra is divided power on the suspension of the generator. And we also know that Tor over a truncated polynomial algebra is exterior on the suspension of the generator times tensored with a divided power algebra on a class called the transpotence. So what all of this means is, given the homology of the nth space, we can at least write down the E2 page of a spectral sequence computing the next space. So that's great, but clearly doesn't allow us to finish the computation. But there's some tools we haven't used yet. Namely, we haven't used the circle product structure. And this circle product is induced by this map on the spaces. And this map can be defined very explicitly on M. So let's assume that the circle product for some Km and Kl has been defined. Then we'll replace Km plus 1 and Km plus L plus 1 with their bar constructions. So here we have B, this is BKM, and here we have BKM plus L. And we're going to define this map by keeping the point in the simplex the same and taking the circle product in Km and Kl, which we already know how to do. And what Ravenel and Wilson prove is that this construction is both well-defined and actually gives the desired cup product pairing. So this is great, but I should probably also give you the base case because we can't have an induction without that. So the base case is, so K0 is going to be Fp. So if we have some, let's say, element Y in KL, this is going to end up being Y star product with itself Q times. And this ends up being the right thing to take. So we have this circle product structure, and we can write it very explicitly in terms of the bar construction. And this is useful for the following reason. Thomason and Wilson are able to prove that the circle product factors through the bar construction. And this means that the map on the associated graded pieces can also be described inductively. And what this leads to is additional structure in the bar spectral sequence, specifically compatible with the circle product in E homology. There is a pairing going from the bar spectral sequence tensored with some homology that we might know to the bar spectral sequence for BKM plus L. And moreover, this pairing has a very explicit formula on the E1 page, which can be computed using the iterated reduced coproduct. So it's something very tangible that you can write down. And with this, Ravenel and Wilson are actually able to identify everything that is in the Tor term in terms of circle products of elements in homology that they already know. So an example of what this does, well, let's start with the homology of K1, which we've just said is exterior on a generator E1 and truncated a polynomial on some generators alpha I. Then computing the E2 page, this exterior algebra is going to turn into a divided power algebra on the suspension of E1, which I'll call E2. And this truncated polynomial algebra turns into something that's exterior on E1, the suspension of the alpha i's, and divided power on the transpotence. So this is our E2 page. And then from there, these elements are given names which come from CP infinity. So then we need to identify circle products to prove that everything on this E2 page is in fact a permanent cycle. So nothing could support differentials. These elements end up coming from CP infinity. So these are a little bit of an exception in that they're the only thing that isn't coming from circle products, but the rest of the inductive argument after this, it's all circle products. And then the E1 suspension is simply the same thing as circling with E1. And then using the bar spectral sequence pairing, you can compute that divided power on this transpotence really, in fact, corresponds to something that's truncated polynomial on circle products of these two generators. So the upshot of this is that we can inductively deduce the homology of Eilenberg-MacLane spaces using standard homological algebra, which is really cool. So because this will be relevant to the C2 equivariance story, I'll show you what the Ravenel-Wilson answer is written down. So we have E1 living in the degree 1 homology of K1, alpha I lives in the 2I homology of K1, and these are the generators beta I coming from CP infinity. So here we're supposed to remember that CP infinity is a KZ2, and as such has a map to KFP2. So that is how these additional generators are coming from. And then our generators are going to be E1 alpha parentheses I, which is going to live in degree 2p to the I, and beta parentheses I in degree 2p to the I as well. And then we need some finite indexing sequences. So we have one that's called I, and here this indexing sequence, everything is strictly increasing. We have a second indexing sequence where everything is just greater than or equal to 0. And we define some elements in terms of circle products using these. And what Ravenel and Wilson show is that the homology of these Eilenberg-MacLane spaces is exterior on E1 circle alpha I, circle beta j, tensored with truncated polynomial on alpha I, circle beta j. And in the case that we're at the prime 2, this can actually be written a little bit more simply. It can be written in terms of circle products of just elements in RP infinity. So we just have circles of E1 and the alpha i's. And then, so this is an unstable answer, a computation that computes the homology of a space, but we could also think of stabilizing to the dual Steenrod algebra. And they also show that if you homology suspend beta sub I, to define some Xi's, and alpha parentheses I to define tau i's, we get the usual Milnor basis for the dual Steenrod algebra. So that's all the background on the non-equivariant Ravenel-Wilson story. Are there any questions at this point before we move on to C2 equivariant? Okay, in that case, we'll continue. So we've been talking about non-equivariant things, but we also want to be studying, doing an equivariant computation in the C2 equivariant world. So we should set some notation for that. So we're going to consider the Eilenberg-MacLane spectrum for the C2 constant Mackey functor F2. And if you aren't familiar with Mackey functors, just think of this as the correct equivariant version of the field F2. So this spectrum consists of spaces with structure maps between them. And now our spaces are bi-graded. They're going to be indexed over the sign and trivial representation. And up to C2 equivariant homotopy theory, HF2 is also characterized by the homotopy classes of maps from X, the cohomology of the space X being the homotopy classes of maps from X into KB. And this means we're going to have a notion of the star product. Additionally, HF2 is a genuine equivariant ring spectrum, so we have a circle product. And that means we can at least investigate what these two products do under homology. So the strategy and equivariant computational tools that I've been using is to give explicit models for the star and circle product on these equivariant Eilenberg-MacLane spaces. And I do that using bar and twisted bar constructions. I then investigate ROC2 graded bar and twisted bar spectral sequences, recovering the examples of the homology of K sigma and KZ rho, where here Z is the C2 constant Mackey functor Z, and rho is the regular C2 regular representation. So rho is equal to 1 plus sigma. And then also compute KZ2 sigma, which would be a new example. So these bars of spectral sequence computations are great, but they also turn out to be rather complicated for the signed Eilenberg-MacLane spaces. In fact, as we'll see, that there's evidence of arbitrarily long equivariant degree shifting differentials. And for this reason, it's helpful to include an additional approach as well. So Mark Behrens and Dylan Wilson have this lemma that says that if we have a C2 spectrum X and a collection of elements B sub I that are elements of the ROC2 graded homology of X, satisfying the two properties that on the underlying level, they form a basis for the underlying homology, and taking C2 geometric fixed points, they also form a basis for the homology of the C2 geometric fixed points of the spectrum, then the homology must be free, and moreover, the collection of elements you started with is a basis. So the computational strategy I use is to use circle products to produce elements in the homology of KV, starting with the homology of some spaces we know, and then use explicit models for the star product and circle product to analyze the underlying and fixed point maps. So first, in order to talk about the twisted bar construction, we'll need a definition. We'll need to define the notion of a twisted monoid. So a C2 space A is a twisted monoid if it's a topological monoid in the non-equivariant sense, and it has this additional condition that if gamma is your generator of the group C2, gamma acting on a product XY is the same thing as gamma acting on Y times gamma acting on X. So if your monoid is commutative and has the trivial action, for example, this is one example that satisfies this, there are many more. Okay, so if we have a twisted monoid, we can then define the twisted bar construction. So I have this written down, but in terms of our geometric model, I like to think of it this way. So we still have points in our interval. So this is still the interval -1 to 1. And so points in this twisted bar construction will look like points in our interval with labels in A. but this now has a C2 action. And our non-trivial element acting on this essentially flips this around the origin. So T3 is going to go to negative T3, and gamma will act on the label. T2 goes to negative T2 with our group action on the label, and T1 goes to negative T1, and the group acts on the label. And this is topologized in the same sort of way with if points come inward in the interval, you multiply them, and if they go off to the boundary, you identify them with identity, but it has this additional action. And this is also nice because we can talk about the star product in the same sort of way where it is once again overlying these two intervals. So, oh, and then the other thing that's important here is, so this bar construction we denote by B sigma, and B sigma is a trivial representation d-looping functor. So that means that if we apply B sigma to some Eilenberg-MacLane space KV, we'll get the V plus sigma Eilenberg-MacLane space. So this allows us to proceed by induction in the sign representation direction. So that's great, but we want to be doing computations. So we probably want to be considering the twisted bar spectral sequence, which we certainly can do. It has a similar filtration to as in the non-equivariant case, but the associated graded pieces are a little bit different. We now have a representation sphere smashed with T copies of our monoid, and these T copies have a C2 action, but we can again apply homology to this, and this will give us a best spectral sequence computing the ROC2 graded homology of B sigma of A. So that's great. Let's see how this works in computation. So in this example, we're going to be computing the homology of B sigma K0. So here K0 is F2. This is going to be the same thing as the homology of K sigma, which is the same thing as the homology of, sometimes people call this twisted RP infinity. It's the space of lines in an infinite number of copies of the regular representation. So we're going to prove that it's a free over the homology of a point with a single generator in each of these representation degrees. And we'll begin with the E1 page and proceeding by filtration. So something that's a little bit different in ROC2 graded spectral sequences, you have to decide, well, your homology is now bigraded, so you have to decide, do you want to draw your pictures bigraded with respect to your representations or filtration? And in my pictures, filtration will be kind of invisible, and then we have the number of sign representations on the vertical axis and total topological degree on the horizontal axis. So the E1 page of this, at t equals 0, our filtration 0, we get just one copy of the homology of a point in degrees 0. When t equals 1, we get one copy of the homology of a point in degree sigma. So now we have a copy of the homology of a point here, and then another copy lying here. Adding on t equals 2, we get a copy of the homology of a point in degree rho. And something we can notice at this point in this particular example is that the topological degree is corresponding to the filtration degree. So this was at t equals 0, t equals 1, t equals 2. And something about differentials, well, they can only decrease by 1 in filtration. So any dr differential could at most hit something that's one spot behind it. And so this means that there can be no non-zero dr differentials for r greater than 1. And then considering the case of if we had a D1 differential that hit this possible generator, if we did, that would kill off this entire double cone. So that would be gone, and we would have no more generator left in degree 1, which would kill off a generator of the underlying homology of RP infinity. So we'd arrive at a contradiction. So in fact, this spectral sequence collapses, and we arrive at this picture of the homology. So we have a generator in degree sigma, which I'll call E sigma, and then I'll call this generator in degree rho alpha parentheses 0. And I'll giving these sorts of names to kind of remind us of, in the non-equivariant setting, the generator in degree 2 was called alpha parentheses 0. And if we work a little bit harder, we can figure out the multiplicative structure on the homology of K sigma. It turns out to be exterior on these generators E sigma and alpha bar parentheses I, which live in degree 2 to the I rho. And it has a coproduct formula. The coproduct is a bit more complicated than in the non-equivariant case. We get some additional terms where we see the distinguished elements A and U from the homology of a point coming up. So that's a nice example. So some other examples in which this twisted bar spectral sequence collapses is in computing. So we just did the homology of RP infinity twisted. We could also do twisted CP infinity, and then KZ 2 sigma collapses as well. So that's great. From there, we would maybe want to compute the homology. So this would be a picture of the twisted bar spectral sequence for computing the homology of BK sigma. So we'd want to compute the homology of K2 sigma. And here in this picture, X is defined to be E sigma. So the degree of X is sigma, and Y is defined to be alpha bar parentheses 0. So the degree of Y is rho. And this was just because down here, writing the parentheses took up a bit too much space. So what ends up happening is in the twisted bar spectral sequence, different representatives that are fixed by the C2 action. So here we have some bar representatives in blue. These support a full copy of the homology of a point in shifted representation degrees. So that's great. Those that aren't fixed by the C2 action end up supporting like a single line. And well, this picture is clearly not a free picture at this point because we have a lot of things that are not shifted copies of the homology of a point. So we can prove that there is a D1 differential as well as a hidden extension, which kills off this portion of this double cone and forms a new one in this representation degree. And this specifically detects this star product element. And there's some similar D1 differentials further on, but specifically this D1 differential, well, if we expect this to be free, in the underlying setting, what is supported by this bar representative gets killed off non-equivariantly. So we would, if it works the same way, we would expect this to be killed off equivariantly as well. But there's nothing in this degree that can hit this full cone. So from this D1 differential, there should be, this D1 should induce a D2 differential that should kill off the rest of this cone if we already knew this is free, which I haven't told you that it is yet. But this is the sort of structure that you end up seeing in this twisted bar spectral sequence. So it very quickly becomes something that's more complicated and then perhaps a bit unwieldy to deal with. So this is where one option is to return to the Rabinel-Wilson lemma, to return to the Mark Behrens and Dylan Wilson lemma, computational lemma. So we have the homology of K sigma. So something we could do is just take circle products of the homology of K sigma and check on the underlying and fixed point levels, does this map to the right homology? Because if it does, we've produced generators and these are actually form a basis. And that turns out to work. So we can take finite sequences and these circle products, and it turns out to be the case that the homology of all these spaces, K sigma, is exterior on these generators. And we can also compute the homology of K rho in a similar sort of way. So we need some additional named generators coming from KZ rho. So these get the name beta bar parentheses I in analog to the beta i's in the non-equivariant setting. And the homology of K rho is exterior on these generators. So something that's interesting to notice is for these sign representation spaces, this answer ends up mirroring the non-equivariant answer at the prime 2. However, when we begin working with mixed representations, we have these additional generators and we have an answer that's looking a bit more like the non-equivariant answer at odd primes. So from K rho, we can move on to having one sign representation plus a number of trivial representations. So we can continue doing trivial representation de-loopings on this. So something we can observe is that there's also an equivariant version of the Thomas and Wilson theorem that the circle product on these equivariant Eilenberg-MacLane spaces also factors through the bar construction, and the map on these equivariant associated graded pieces can also be described inductively. And this leads to a circle product pairing in the ROC2 graded bar spectral sequence. And this can be used to compute the homology of all the spaces K sigma plus I. This involves, to write this down, what the answer is, you need a fair bit of notation. So some indexing sets, I, W, J, and Y, and then defining circle products out of all these elements. But if you do that, then you're able to write down very explicitly what the homology of all these spaces is. So from there, you'd hope that, okay, so we did that for K sigma plus I. What about K2 sigma plus star, and so on? Well, so far I've encountered a little bit of a complication in doing that, in that on the E2 page, it's no longer true that all of the elements that come up in the TOR term are identifiable in terms of circle products. And this is true for degree reasons. Also, it's not yet totally clear if the spectral sequence collapses. So the only possible thing would be some differentials maybe hitting negative cones. So that these cases are like a little bit less clear at the moment. But I do have a conjecture for these spaces, and my conjecture is that I believe the RC2 grade homology on these spaces is presumably exterior on the generators given by the cycles on the E2 page. So equivalently, the RC2 graded bar spectral sequences computing this homology collapses. So two possible proof strategies I'm thinking about right now are dualizing my answer for the K sigma spaces and then using the equivariant version of the Borel theorem. What's a little bit tricky about that is in dualizing my answer, I would need to make sure that my generators are transgressive, so I can use the Serre spectral sequence, and that's maybe a little bit complicated. Another thing I'm thinking about is Cronholm's freeness theorem, and so that applies for finite type complexes, and perhaps that might imply that the homology really is free for some of these spaces that I wouldn't know is free otherwise, and perhaps that allows me to deduce some differentials as well. And so some future directions from here are, well, Ravenel and Wilson in their non-equivariant work have that the homology is the free Hofring on the homology of K0, K1, and CP infinity, subject to a single relation. So I'd like to be able to write down a similar statement in the C2 equivariant case and really understand this global structure of Hofrings that do arise there. And then Hill and Hopkins also have an extension of Ravenel and Wilson's construction of a universal Hofring over mu star. And I'd like to understand maps from that construction into the homology of the spaces I've computed. And then also sort of by, well, exactly by construction, these elements beta bar parentheses I can be homology suspended to define C i's and the alpha bar i's to define tau i's. And we know how those map into the C2 equivariant dual Steenrod algebra, but something that's not at all clear is what an arbitrary element in the homology of K2 stabilizes to. So we know it for some specific generators, but otherwise not completely clear. And then it's also not clear how this unstable relation, how this stable relation arises from the unstable story. So there's definitely more to understand there as well. And then the E2 page of the bar spectral sequence is a Tor term. So it'd be nice if we could write down the twisted bar spectral sequence or some version of a twisted bar spectral sequence in terms of a twisted Tor and understand the homological algebra side of this problem a bit better. And then besides that, there are a few computations that could be done with the real Morava-K theory of C2 equivariant Eilenberg-MacLane spaces, the ROC2 graded homology of the spaces of the real Brown-Petersen spectrum, and then generalize to odd primes where we might not, or likely may not have as much freeness as we do here in the C2 equivariant case. And then a bit dually to the twisted bar spectral sequence, it would also be interesting to do some twisted Eilenberg-Moore spectral sequence computations. So at this point, I'd like to wrap up. Thank you all for listening. Are there any questions?
I have a question.
Yes.
So if you take like the, I guess HF2 is a ring spectrum, but it's in G spectra. So if you take homology with it, you should get like a Tambara functor, or like a graded Tambara functor. Do you like the norms anywhere in these sorts of computations, or?
So like the homology should also be a Tambara functor as well. And there's a freeness theorem of Mike Hill's that also like says how that works. And I believe the norms end up being very uninteresting. I believe the norms are 0. So then like knowing the ROC2 graded homology really tells you pretty much everything that's happening. So that seems to be the case in this setting, and that's coming from the underlying homology being exterior seems to really force that to be the case.
Thanks.
Yep. Any other questions? And then I'll perhaps stop the recording here.